Good morning, everyone. So we welcome you all to the fifth day of the course. The topic of this entire day is about space charge. We will discuss. We have 4 sessions on space charge measurements, and the first talk will be given by Dr. Nandini Gupta ma'am on space charge measurements. Thank you, ma'am, and please take over.
Thank you, Kinshuk. Good morning, everybody. So today we are going to talk about space charge measurements in various kinds of scenarios. The first session, which I will be considering, which I will be talking about, I will be talking mainly about the basics of space charge and space charge measurement using PEA. Now, the question that arises at the first instance before we can go to any nitty-gritties is what exactly is space charge? I think many of us are not aware how to distinguish between the 3 different kinds of charges that we are concerned with in the study of dielectrics. First is, of course, free charge. Free charge is accumulated at maybe, let's say, across dielectric materials and even near dielectric materials, but the dielectric material, as long as it has its insulating property, will prevent the flow of free charge through it. But of course, some amount of free charge does flow through dielectrics, which contributes to losses. So that is the role of free charge with respect to dielectrics. Secondly, we need to consider bound charges. Bound charges are the charges within the dielectric which causes polarization. We've talked at great detail about polarization yesterday. So to give you an idea about what I mean by saying that bound charges contribute to polarization, consider the most basic kind of polarization that Dr. Patel talked about yesterday. You have an atom is neutral in the absence of an electric field. When you apply an electric field, the nucleus, which is positively charged, remains where it was, but the electronic cloud deviates along the direction of the field so that the negative charge center is deviated from the positive charge center. This results in the formation of a dipole. And with all kinds of polarization mechanisms that we discussed yesterday, this kind of charge separation is going to happen in the presence of an applied electric field. But these charges will result in a layer of induced negative charges near the positive electrode and a layer of induced positive charges near the negative electrode. However, the difference between free charges and induced charges is that they are bound charges. What I mean by bound charges is that you may see them as isolated positive charges or isolated negative charges in their effect on the electric field. However, they will never be able to travel through the dielectric. They can only move around their equilibrium position in response to the electric field. And therefore, the bound charges are the charges that are responsible for polarization, and therefore bound charges are responsible for the permittivity of the dielectric medium. So this is about free and bound charges. We now talk about a third kind of charges which are very relevant in the study of dielectrics, and that is the space charge. Those of you who attended the question and interactive session with Professor Raju yesterday evening would remember him talking about space charge being the accumulation of a charge of a certain polarity in any position. So let us imagine that somewhere within the dielectric, there is a lot of positive charges accumulated, or there is a lot of negative charges accumulated. This is space charge accumulation. And therefore, the point that I need to make very clearly here is that when we are talking about space charge, we are talking about free charges. These charges are free to move from one point to another, which means the energy levels of these charges are in the conduction band. They have enough energies so that given an opportunity, they would be able to travel from one point to another within the dielectric. But for whatever reason, there are constraints in one particular location, and as a result, we call it space charge accumulation. So to repeat, space charge is free charge, which is conglomerated in a particular location. Now, you would actually find that space charge is not something which is completely new to you. You have discussed, I mean, those of you who are students of high voltage engineering would have accosted space charge somewhere or the other. In fact, in this course, we have not really talked at great detail about breakdown mechanisms, especially in gases. Space charge is what causes the transition of Townsend discharges into streamer discharges. Space charge accumulation is what is responsible for trickle pulses in corona. If you remember, we have not discussed in this course. When you have partial discharges on transmission lines, we call it corona. And depending upon whether the high voltage electrode around which the non-uniform field happens, depending upon whether it is positively charged or negatively charged, you will have different kinds of corona. If it is a positively charged electrode, which results in corona, you will see a whitish glow, uniform whitish glow around the electrode or the transmission line. Whereas if it is negatively charged, you will see some pulses, you will see some blue pulses. And these are called the trickle pulses. So it is space charge which results in the different kinds of corona that you have under positive polarity and negative polarity. So space charge actually is not a new concept, but what is probably a new concept to most of you is the behavior of space charge and the effect of space charge in solid dielectrics. So as I say in the first sentence here, space charge occurs whenever the rate of charge accumulation is different from the rate of removal. So at any point in the dielectric, if there is a lot of charge flowing in and not sufficient number of charge being removed, what would naturally happen is you would have an accumulation of charge. Now, this accumulation of charge at a particular position may be of both polarities, but what would happen is you would probably have one polarity which exceeds the other. Before I go on to discuss more about space charge, what I would like to mention is why are we at all interested in the study of space charge? Can you ask them to stop hammering?
Yes, ma'am.
Somebody is asking a question. Naresh is asking the question, what does the term space in space charge mean? Yes, you could say that it means bulk of the material. That is, there is a lot of charge accumulated in a particular space. I mean, this is my interpretation because that is what it means. Why it came to be called space charge and why didn't they call it some other kind of name, I wouldn't know. But yes, you can translate these to mean that there is a particular position, and in that particular position in space, a lot of charge is accumulated, and that's enough to brand it space charge. But then to come back to my question, why are we at all interested in, what did I do? Why are we at all interested in space charge as a completely different, why do we need to invest one day in space charge? The reason is this, which I've already mentioned to you several times in the course of this various lectures that I gave. When you have a dielectric, of course, you are looking at the application of an electric field. When you apply an electric field, the dielectric material is stressed. But in addition to that, be it gas or be it solid or be it liquid, if you have an excess number of charges located anywhere, even if you have one, this charge would behave like a source of field, and therefore it would exert its own field on the existing applied field. So you have a situation where the applied field is present, and on top of the applied field is superimposed a second field due to the charge. So the applied field is called the Laplacian field, and the charge field is called the Poisson field, because you need Poisson's equation to solve for the space charge field. Now, given, depending upon the direction of this space charge field with respect to the applied field, either the existing field may be exacerbated, that is, you add to the field, or the field may be mitigated, you might lower the field, depending upon the direction of the space charge field. If it exacerbates the field, it means that the dielectric material, under the application of a certain field, sees a higher electric stress in the presence of those space charges. Whereas if the space charge was absent, the field would have been lower. The consequence is very easy to understand. Breakdown will be reached earlier. At lower fields, the material will tend to break down. But there is another consequence, which will be, I think, discussed in the lectures, but let me still touch upon it. The most important consequence of space charge accumulation in solids is, I'm going to limit my discussion to solids, because if I start talking about gases and liquids, there are so many other processes which may come into the picture. So I just want to stick to a discussion on space charge and not the associated phenomena. So when you have this kind of field exacerbation due to a space charge, what really happens is this: beyond a certain amount of space charge, below a certain applied field, space charge does not accumulate within a material and everything is hunky-dory. But beyond a certain critical field, and this critical field is called the space charge threshold field, or the threshold field for space charge accumulation, space charge will begin to accumulate within a material. So once the space charge begins to accumulate within a material, what you have is the material begins to see higher and higher electrical stresses at the same electric fields. And this causes electrical degradation. In the lecture on aging, I talked about degradation mechanisms and damage mechanisms, where certain processes happen, physical and chemical processes happen within the dielectric, which do not show up as visible signs of defects, but which causes continuous degradation of the material, causes aging. In fact, space charge accumulation can be considered as an aging marker, because firstly, space charge accumulation causes aging, and when a material ages, the space charge accumulates more. So in this respect, it is somewhat like partial discharges, that it is a marker of the age of the material. At the same time, it is also a cause for further aging. And this is especially of interest because right now we are increasingly looking at HVDC applications. So when we have DC fields applied for very long, high DC fields applied for very long periods of time, space charge becomes very, very important. And that is why you will see that increasingly there is a lot of research going on in space charge, and a lot of research we'll find in this area in HVDC cables. Now, let me come back to the theory. We can discuss these issues later. Some of these issues will be taken up during the course of the day. So space charge accumulates faster than it can be removed. Where does this charge come from? If you're going to accumulate charge, charge has to come from somewhere. Charge can come from several sources. Charges can be injected into the material from the electrodes. They can be generated within the material through chemical processes or through ionization processes. Trapping and detrapping of charges. This is something that I will discuss in the coming slides. How charges can get trapped in the material or can be released from traps in the material, which is called detrapping. Drift or diffusion through the volume. So these are all processes by which charge can arrive at a particular location. When I talk about space charge, I might be talking about electrons. I might be talking about ions, positive as well as negative ions. It depends upon the material. It depends upon what is the transfer mechanism which is causing charges to drift through the material. Space charge arises both due to moving charges and trapped charges. Moving charges are moving, arrive at a particular location and decide to hang around there, decide not to go forth. I mean, of course, there must be conditions which make it do that. These are mobile charges. And then there are trapped charges, which are actually not even free to move. They are trapped. What do I mean by trapped charges? Let me come to that point. Any questions which are not necessary to the understanding as I go along, I'll take up later. You can keep posting your questions. Now, what do I mean by traps? If the charges are going to be trapped, there have to be trapped somewhere. What do I mean by traps? Now, here I'm going to go a little bit into the physics. Imagine there is an electron, and this electron is flowing through the material. The electron is flowing through the material. Now, when an electron is in a particular vicinity, what would happen is, because an electron is a charged body, it would result in a charge disturbance in a very small region. In the sense, you have the neutral molecules and an electron arrives there. So the electron causes other electrons to be repelled. It causes the negative ions to be repelled. It causes the positive ions to be attracted. So what you have is, in a very small region, you have a local disturbance of the charge scenario. And when you have a local disturbance of the charge scenario, you can imagine that this is a kind of polarized cluster which is formed. So there is a very small region around the electron. An electron is a very, very small particle. So we are talking about absolutely macroscopic situation where you have a small electron, and around that electron you have a kind of polarized region. Let us call that kind of a polarized region is called a polaron. Now, as the electron continues to travel through the medium, this polaron moves. So as one polaron is created, and then the electron moves on. When the electron moves on, this polaron that it leaves behind goes back to its equilibrium situation. So it is again a neutral state. But where it arrives, it creates another polarization situation, and the polaron is created. So it's like the polaron is traveling with the electron. So basically, the regular array of atoms which you have under equilibrium situation is getting disturbed, and this disturbance is moving with the electron. The polaron in this case behaves like a negatively charged particle, just like the electron. As the electron is moving, it's as if a charged region is moving around, except that the mass of that polaron is, of course, much higher than the mass of the electron. Now, what is the consequence of this? So this electron is moving, and along with the electron, this polaron is moving. And what might happen is that at a particular site, not at every site, at a particular site, there might be a scenario, because you do not, even in a homogeneous medium, you do not have exactly the same situation. You might have defects, you might have vacancies. So at a particular situation I, what might happen is, because of the polaron, there might be a reduction in the radius of the polaron. How? The trap depth is increased. So what might happen is, there is a trap formation in one particular polaron site, and this particular electron, which was moving freely through the dielectric, might get trapped, because the polaron radius reduces, the electron gets more localized, and that is how the trapping mechanism begins. The electron gets trapped because there is a change in the trap depth. Now here I need to stop and tell you what I mean by trap depth. When I talk about trap depth, or the depth, deep or shallow traps, I'm not talking about heights. I'm talking about energy levels. So these traps are associated with particular energy levels. You might remember that when we, from basic physics, you have the valence bands, and then you have the conduction bands. And there is a forbidden energy gap at the Fermi level, which needs to be crossed for an electron in the valence band to come out into the conduction band. Once it acquires enough energy, an electron which was originally resident in the valence band may come out into the conduction band and may contribute to conduction current. So at that point, it becomes a free electron, free charge, and it is free to travel. It contributes to mobile electron. It becomes a mobile electron. Now, what might also happen because of defects, because of impurities, there might be in the lattice several vacancies which have trapped energies, which have energies which are not as low as that of the valence band, but lower than the conduction band. So when I say an electron is trapped, what it means is that the electron gives up some amount of energy and it arrives at an energy level which may be very close to the energy level of the conduction band, just below the conduction band. So in that case, we will say that the electron is trapped in a shallow trap. What does it mean? It means that if an electron is resident in a shallow trap, if you provide that small energy that it requires, the small energy difference of the trap level from the conduction band, that energy will be much smaller than the ionization energy, and that energy can be acquired from the field, and the electron can detrap and begin to contribute to free current. Similarly, there might be deep traps. Deep traps are, of course, again, energy levels which are much lower, they're closer to the valence band. They are far from the conduction band. So obviously, deep traps, if an electron is trapped in a deep trap, it will need more energy to be able to come out of the conduction band. So this is the difference. So that is what I mean, that these kind of trap levels would be created because of the reduction in the radius of the polarization, and as a result, the trap depth will be increased and the electron will be trapped. And so this is a kind of hint of how these trapping centers might be created, and these trapping centers result in trapping of charged particles. If you have centers which are associated with anion vacancies, we call them passive centers. If these are associated with cations, we call them active trapping centers. So to put it in a nutshell, when an electron travels through a particular material, due to the presence of the situation, the damage, the degradation, the local situation within the dielectric, some of these electrons may get trapped. Trapped means they will be removed from the conduction, they will lose some of the energy, and they will reside in an energy level which is lower than the energy level of the conduction band. So they will sit there till they acquire enough energy to detrap and then again contribute to the conduction current. So if you have a lot of traps in the material, you will have a situation where a lot of charges will accumulate, and as a result, you will have the space charge field. Before I go on to the space charge field, let us look at some of the conduction mechanisms that are present in dielectrics. Firstly, let me talk about low field conduction mechanisms. If you talk about low field conduction mechanism, very often we don't remember the conduction that you have in dielectrics is nothing but the V equal to IR, which is the ohmic conduction, which means the voltage current relation tends to follow the Ohm's law. Of course, in dielectrics, the current will be very small because the resistivity is very high, but no matter, it is the conduction current that you have in conductors, the process is absolutely similar. Except that in dielectrics, you are not only concerned with the current flow due to electrons, but you are also concerned with the ionic conductivity, because the electron conductivity and the ionic conductivity might be comparable in dielectrics, which is not the case in conductors. Now, the thing is, if you have a lot of traps in a dielectric, it means that as the electrons or the ionic carriers, give me a second, I'll just switch on the fan. Yeah, So the point is that if you have a current flowing through the material and you have a situation that there are lots of traps in the material, what it would mean is that some of the charges, as they're flowing through a material, would get trapped. So what are you actually doing? You're actually removing charge carriers. So you start in the right at the outset, you have low number of charge carriers because it's a dielectric. And the charge carriers have enough resistance, so they're not really able to flow through the material very well. And you are removing players from the game. So effectively, trapping reduces the number of carriers which are available for conduction and therefore reduces mobility. This is what happens in case of low fields. Now, as I said, in case of dielectrics, it's not only the electrons which are responsible for charge flow, ions are also responsible for charge flow. What do I then mean by ionic conductivity? In case of ionic conductivity, I'm talking about the movement of a vacancy through an ionic lattice. So you have a charge electron missing and you have a vacancy which is positive, and it is this vacancy which propagates through the material. At low fields, you will find that the ionic conductivity also follows a ohmic relationship. But when you go to higher fields, the behavior becomes super ohmic in the sense that it no longer follows the Ohm's law, but current increases at a faster rate with voltage than that is predicted by Ohm's law. I'll come to this point later. I'll come back to this. So therefore, we are talking about a trap limited mobility where the mobility is kind of restricted by the presence of traps because the traps are removing some of the carriers. So let's say you start with NT, this total number of charge carriers, you will land up with, NT is the number of trapped charges and NC is the number of mobile charges. So you will end up with a ratio theta of NC to NT. And this is given by this relationship where capital N is the effective number of traps and NT is the number of traps that are present. Delta ET is the trap level. So we are talking here about a single trap level, just to illustrate. So what I mean here is if you look at this picture, you see that there is the valence band EV, that is the energy level for the electrons to be present in the valence band, in which case they're bound charges. And then there is the EC, which is the conduction band. So you require to have enough energy, that is EC minus ET, EV, to be able for an electron to be able to come from the valence band into the conduction band. When it arrives at the conduction band, it is able to flow through the material and contribute to conduction current. But what we are talking about here is ET. ET is a trap level. Here I'm talking about a single trap level. You might have several trap levels. So there might be very many this kind of dashed lines. Look at this ET. The difference between EC and ET, which I have marked as delta ET, is a very small energy difference compared to the energy difference between EC and EV, which is of course the Fermi level. So therefore, you can imagine that if an electron is resident on ET, it might be quite possible for it to acquire either from the electric field or maybe from thermal field or any other kind of energy that is present in the medium to acquire the field, acquire the required energy to be able to transcend this delta ET and come to the conduction band and become mobile. At the same time, there is enough possibility for an electron to lose this delta ET and become trapped and be removed from conduction. And so when you have a lot of these traps getting filled up, the mobility changes. Ordinarily, and this is also dependent on Kb, which is the Boltzmann constant, and T, the electronic temperature of the material. So theta is generally in the range of 10 to the power minus 10 to 10 to the power minus 6. So this is the kind of number. So what you have is you are reducing the number of charge carriers which are available for conduction. This is also equivalent to say that the charge carriers will spend a larger time within the material because it will spend time in the traps rather than in the conduction trap. So that is why we call it trap limited mobility, because the ratio of the number of carriers which will be removed from the conduction band will approximately increase the time taken for the charge carriers to travel this distance if compared to if there were no traps present. So what I'm trying to say is that this change in the number of charge carriers is looked upon as an increase in the time of conduction for a particular charge carrier. The effect is the same, and this is what is meant by trap limited mobility. Now, similarly, let me come to high field conduction mechanisms. When I talk about high field conduction mechanisms, there are two kinds of conduction mechanisms that I'm talking about. I've already mentioned that I'm no longer talking about electronic ohmic conduction, because at high fields, when lots of charge accumulation takes place, it is no longer Ohm's law, the VI relation no longer holds. And what we have is space charge limited conduction. It means that there is a lot of space charge accumulated. It's like trying to move through a crowded room. A particular charge enters a place where there are lots of space charges trapped and already present. They will prevent the electron from moving through the material. So charge injected into the bulk from the electrodes under high fields may find it difficult to move through the bulk due to traps. And therefore, the conduction becomes very low. And this is called space charge limited conduction. A second kind of conduction mechanism is possible at high fields, and that is field limited space charge. The drift velocity of the injected carriers, be they electrons or holes, become a nonlinear function of the high fields. So it is no longer proportional to E. We knew that velocity is proportional to applied field E. This no longer holds at high fields. And therefore, you might even find a negative differential. That means it may seem to be moving in the opposite direction. And as a result, in the space charge region, you tend to exacerbate the field very highly. And therefore, what you have is space charge begins to accumulate much at a higher rate because of the field exacerbation. So in one case, first space charge accumulates. Because space charge accumulates, further charges see an hindrance to the flow. And when they see a hindrance to the flow in high fields, the space charge continues to accumulate. This is space charge limited conduction. In the second case, because of the space charge, because there is a high field, this high field results in the resistance becoming even negative, becoming very small, and sometimes even becoming a negative differential resistance phase. So the individual charge carriers tend to accumulate further and the field exacerbates further. So this is the situation that you have in high field region. So therefore, it becomes important to realize that not only the field scenario will change drastically in the presence of space charge, but also that the space charge in itself will cause degradation of the mechanism. This is not something that I'm discussing in this lecture, but this is what we have seen in the course of our research, that the accumulation of space charge causes degradation of the material. And therefore, it is needed for us to be able to measure space charge. And I will repeat here, it is important to measure space charge because we want to find out how much space charge is accumulating, because we would like to understand how the conduction will behave, how the mobility will behave, how the material will behave, but also because if we can measure the space charge we have published to that effect, that space charge accumulation can be used as an aging marker. So you can measure space charge and you can compare the space charge between two materials, and you can say, look, this is a more aged material and it is reaching its end of life. So the objective of space charge measurement is to measure the charge intensities and their polarities, because we need to understand how the fields will behave in the presence of space charge to determine the trap level. So what are the levels at which charge accumulates? And what would be the space charge distribution in the presence of a particular electric field? And we also understand that the accumulation of space charge will determine the mechanisms of polarization and conduction. And therefore, we need to understand what is the behavior or the distribution of the space charge that has accumulated not only on the surface. The surface charge is easy to measure. Somebody asked me a question whether below threshold field we can call space charge surface charge. No, surface charge is the free charge which is present on the surface of a dielectric material. And space charge is present within the volume of the dielectric material. Surface charge would be free charge, which would have energy levels close to the equal to that of the conduction band. Space charge has energy levels lower than the conduction band. So there are various techniques for charge measurement. I will not go into all of them simply because I do not have practical experience with those techniques. You can look them up in any book on space charge measurement. I will talk about the particular space charge measurement technique that we use in the laboratory, which is the pulse electroacoustic measurement. This is the schematic that you have. What you have is, this is your sample. This x equal to d and x equal to 0 are the electrodes, and sandwiched between these two electrodes is the sample. It's a thin sample. In fact, okay, the practical issues will be discussed later. Oh my God. So what you have is within the dielectric. So if you look at this picture, this diagram at the bottom, this shows that there is a lot of charge distribution within the thickness of the material. So as you go from one electrode to the other electrode, you should see a difference in the charge distribution. There should be a particular charge distribution. So let us imagine this is the kind of charge distribution that you have. Now, in pulsed electroacoustic measurement, what you do is, of course, you energize the material so that space charge can accumulate, and the material has to be energized at fields above its threshold field for space charge to accumulate. Any small field will not cause space charge accumulation. So you energize the material with a DC field because we don't want any polarity reversal to disturb our measurement. So the field will be constant throughout our measurement. At the same time, what we do is we apply an additional pulsed electric field. Now, what this pulsed electric field does is it induces a perturbation on the space charge. So there is a pulse electric field and the space charge gets perturbed. Now, whenever a space charge gets perturbed, so let us imagine that at a particular location, there is some space charge. Let's say this is the space charge delta sigma, which is present at a particular very infinitesimal thin layer. Now, when I apply the electric field propagates through the specimen, and when it reaches this position, it perturbs the space charge in this position. When the space charge in a particular position is perturbed, it causes an acoustic wave to be generated, and this acoustic wave propagates through the sample. So it is not the space charge which is moving through the sample, but an acoustic wave which is proportional to the perturbation of the space charge. So the nature of the acoustic wave is determined by the distribution of the space charge within the thickness of the material. This acoustic wave travels through one electrode to the other electrode. At the other electrode, which is the ground electrode, we have a piezoelectric sensor. And this piezoelectric sensor converts this displacement. The acoustic disturbance is measured as a mechanical displacement, and it is converted into an electric signal. And this electric signals will then be amplified and read as the voltage wave. So the effect is that we have a sample. Within the sample, we have a space charge distribution. We energize the sample with a DC field in order to create the space charge distribution. In addition, we apply an external pulsed electric field. This pulsed electric field disturbs the space charge about its equilibrium position, and at every point as the space charge is disturbed, the acoustic wave is fashioned. So the acoustic wave that travels through the medium will see a disturbance which is related to the space charge distribution. This acoustic wave travels through the material, reaches the piezoelectric sensor at the ground electrode, and is converted into a voltage signal. This voltage signal will be representative of the space charge distribution through the thickness of the material. When I talk about space charge thickness, I am talking about a film like this, a thin film, and I'm talking about this thickness. So distribution along this very, very fine thickness is what we are looking at. Now, when we do this kind of measurements, obviously there are certain assumptions inherent. These assumptions are that the space charge distribution in the dielectric is one-dimensional. We are not able to measure any distribution difference along this axis. It will only be into the paper or into the dielectric. The generated acoustic wave shape in each charge layer is the same as that of the applied pulsed electric field, which is all right for thin films. Every frequency component of the acoustic wave propagates through the dielectric with the same velocity and without decrease in amplitude during the propagation. That means we are ignoring any attenuation or dispersion of the acoustic wave. We are assuming that the acoustic wave, which we need to measure, the acoustic wave has the same constant velocity throughout the material thickness from one end to the other. And we also assume that the linear superposition principle is applicable if there are two or more acoustic waves. That is something we don't need to discuss at this basic level. So what I will do now is, this is about the theory, the basic theory of space charge measurement using pulsed electroacoustic methods. What I will now do is I will very briefly present some of the preliminary work we did many years back, because there will be talks in the course of the day where people will talk about their researches. But right now I will just give you some very basic idea of PEA measurement in homogeneous dielectrics. This is the work that was done by when we acquired the PEA for the first time in our lab. That was in, I think, 2009 or so. And this work was done by Dr. Supriya Das, who gave a talk yesterday, who is now a professor in NIT Meghalaya. So I will just illustrate the concept of PEA using some basic studies that he did. And in this, I want to talk about charge trapping in homogeneous dielectrics. So we took two materials, just simple materials, thin films of epoxy resin and thin films of polyethylene. Now, what were the sources of charge that we expected? So when we put the material inside a PEA, the charge has to come from somewhere before we can expect it to accumulate. So charge may be injected into the dielectric through the electrode dielectric interface. And most of the time it would be through Schottky injection or tunneling processes. Also, as I said, not only is charge injected, charge may be also generated within the dielectric when you apply electric fields. And because of trapping, by the processes that I have spent quite a bit of time explaining, space charge accumulation will take place. How much space charge accumulates depends on many factors. It depends upon the applied electric field. It depends upon the temperature, material composition, electrode material. So once we decide to use space charge measurements, we need to know what are the parameters that can cause differences in measurements. So this is the picture of the pulsed electroacoustic system. But of course, in today's afternoon lecture, you will see a lab demonstration of this same system. So I don't need to spend too much time on this. The point that I want to make is that the samples are very thin. So these are about 300 or 200 micron thick samples that we had used. And the protocol is a polarization duration of 10,000 seconds, followed by a depolarization of 2,000 seconds. So we have to keep the electric fields, the material energized for considerable time so that we reach an equilibrium situation. And these measurements were done at room temperature. Now, this is the kind of situation that you would see. At the two electrodes, you see two peaks. And these peaks represent the space charge distribution, which means that through the thickness of the material, there is almost no charge. in the thickness of the material, all the space charge is localized at near the electrodes. And because the nature of the space charge is the same as the polarity of the charge accumulated at every electrode is same as the polarity of the electrode. This is called homocharge. So same polarity charge is accumulated, and there is no charge accumulation in the epoxy resin. The reason I'm showing you this particular measurement is that you can see a measurement at 10 seconds and you see a measurement at 20 seconds, and you can see that the nature of charge distribution has changed. This is because when you apply the electric field, there would be some polarization and there would be some mirror charges present in the electrodes. So if you take the measurement right at the outset, right, immediately after energization, you do not get the true picture. The true picture is given by the 20-second line, and this means that you have to wait for at least 20 seconds. That is in case of epoxy resin. For other materials, the count might be different. You have to wait till all other processes have been removed, and the charge that you see is only solely due to space charge accumulation within the material. And from this, you can measure the total trapped charge density, which is taken by integrating the charge distribution over length. So QPXT is the space charge distribution between 0 and L, and it is also a function of time. Now, here we show the field effect. As you apply higher and higher fields, the accumulated charge density increases. We start at 30 kV per millimeter because, as I said, there is always a minimum field that is required before space charge can accumulate. In case of epoxy, if I remember rightly, it is around 18 or 20 kV per millimeter. So to be on the safe side, we took measurements at much higher fields. Yes, this shows the threshold field. As you can see, originally you have a particular slope. Please ask them to stop hammering and stop shouting. So as you can see, originally you have a voltage current relationship. So this is actually charge density and electric field relationship, which is of course nothing but similar to the voltage current relationship. And this has a particular slope. But at a particular field, above a particular field, the slope of the line changes. So therefore, the voltage current relationship has changed. And the point at which the sigma E relationship changes slope drastically is the threshold field. This is how you identify the threshold field. And therefore, all space charge measurements need to be made at fields above the space charge field. And you can see that the space charge field is different for different materials. It is lower for polyethylene and higher for epoxy resin, which means that if you were thinking of, if you're trying to choose an application where you are free to use both polyethylene and epoxy resin, which may not be the case, and if you wanted to choose, you would definitely choose epoxy resin, because epoxy resin has a higher threshold field for space charge accumulation, and therefore space charge accumulation and any defects, any degradation due to space charge accumulation will happen at higher fields. So you can very nicely operate at lower fields with very minimal aging. So that is the case of material effect. Then we also have the situation that if you have the same material, this is epoxy, and only the electrode material has been changed. In one case, we use gold. In the other case, we use aluminum. And we have seen that the space charge density changes. So you have a higher space charge accumulation if you have aluminum electrodes instead of gold electrodes, where you have the same sample. Which means what? Which means that less charge is being injected in case of aluminum. Sorry. What am I doing? Yes, it means that less charge is being injected into the material when you are using gold electrodes. That is why you will find that in many microscopy and other things where we use charge electric fields to study a material, just like examples of measurement techniques that Dr. Alok Verma mentioned yesterday. We use gold coating on the on the material, on the samples before we do any measurements. So electron material effect. Now, one more important thing that I would like to mention before I finish is that very often, most often, we are not really dealing with homogeneous materials. We have also done studies with nanodielectrics, but I will not discuss this in nanodielectrics in this lecture. But let me at least talk about multi-dielectric system, which is very common, where you have many kinds of dielectrics in conjunction with other. Now, there is a problem when you have interfaces in dielectrics. When you have two different materials, they have two different permittivities, they have two different conductivities. Dielectric interfaces in this situation will lead to interfacial charge. What do I mean by interfacial charge? So imagine that you have let us imagine that you have two dielectrics in close proximity to each other. Now, if they have different conductivities, please, they need to stop hammering. What is wrong with them?
I'm actually, there is no one hammering, some other people making sound occasionally, I think.
No, somebody is doing something systematically.
Because,
maybe it's not with a hammer. I have no idea what they're using, what tool they're using. And when they're not hammering, they're shouting. What you have here is you have a material with a particular conductivity. Conductivity decides current, which means the number of charge carriers which will arrive through one material and arrive at the interface. Now, let's say this material has a higher conductivity than this material. So there will be more charge carriers arriving per unit time at the interface between these two materials than the number of charge carriers which are transported out. And that is because of lower conductivity of the second material. So as a result, there will be charge accumulation at the interface. And so this is called interfacial charge, and interfacial charge will modify the electric field that you see. It will also modify the transport mechanisms. Now, dielectric interfaces are very common in high voltage insulation systems. Some examples of very common interfaces are solid-solid in cable accessories, in GIS where you have solid gas, or in paper oil insulation like in solid liquid. And right now, I'm just talking about solid-solid interfaces where the difference in permittivity and conductivity of the different materials across the interface leads to interfacial polarization. So in this case, what we have done is we have tried to see how this interfacial polarization can be measured and how this interfacial polarization modifies the electric field within the material and changes the space charge accumulation within the two layers. So we have taken dielectric interfaces of two different kinds. I'll explain as I go along. We have low density LDP and we have epoxy. Now, one problem that you expect in PEA measurements using when you have interfaces is this. In PEA measurements, what we have is we have acoustic waves traveling through the material, and we expect the acoustic waves to start from the high voltage electrode and arrive at the sensor, where which will be measured. But if you have an interface, something more is going to happen. I think Dr. Kasim will explain this in greater detail in the next lecture, but let me briefly talk about this. There will be waves which are transmitted through the interface and arrives at the sensor. But there will be also acoustic waves which will be reflected back from the sensor and will reach the interface and be reflected back at the interface. So whenever there is an interface, there will be multiple reflections, and therefore the signal that you register at the sensor will be polluted by these reflected signals. And therefore, you will not be able to figure out what is the original signal and how that relates to the space charge within the dielectric material. So we have to take care of that. And the simplest way to take care of that is to get rid of reflections by proper orientation. I will not spend time on this. Dr. Kasim will definitely talk about this. We also need to calibrate. Again, I'm not going to talk about this. This will be explained to you during the lab demo as well. So we will need to take into account that there will be reflected signals. We will need to take into account that there are noises that are there, and calibration has to be done. Calibration has to be done for the individual materials, and we will have to have separate calibration factors for the two different materials. So having taken care of all this, what we see is we take a material which is epoxy bonded on epoxy. So it is very nicely bonded and there is no gap. And what we see is that originally there is no signal till 1000 seconds of voltage application, which means that the discontinuity is opaque to the acoustic wave that is traveling. But after 1000 seconds, we find that a negative polarity charge. Now this polarity is different from the polarity of the homocharge. So you have homocharge at the ground electrode, homocharge at the high voltage electrode, and you have charge of opposite polarity at the interface. So because this is something that takes considerable time to build up, we are sure that this is interfacial charge. And this interfacial charge has built up because of the interface between epoxy. Now, this is a little puzzling because epoxy on both sides of the interface would have the same conductivities and same permittivities. Why do we still have interface charge? This interface charge therefore probably builds up because of the surface conditions of the two layers at the interface. When we have different materials, definitely originally, remember, we see a charge accumulation. Remember, this cannot be space charge because we are operating here in this particular case at only 10 kV. And 10 kV is lower than the threshold field for either epoxy or polyethylene. So it can't be space charge. So it is not related to charge. So why do we still see this signal? We see this signal because of the difference in acoustic velocities, or the difference in velocity of the acoustic wave through the different materials. So even if there is no charge, just because there is a discontinuity, you see this. So here you are being able to detect the interface and not the interfacial charge by this peak. When you have interfacial charge, this is what you have. This is the amount of interfacial charge that is predicted by Maxwell-Wagner behavior. Remember, what you will actually see may not be exactly what is predicted by Maxwell-Wagner, because Maxwell-Wagner does not take into account the surface properties at the interface, and there may be more reasons that cause trapping or accumulation of charge in the interfacial region, even at low fills. So as you can see, at 10 kV per millimeter, you do begin to see some amount of interfacial charge accumulating. Of course, applied fields, even for multi-dielectric systems, you have an effect of applied field. Higher the electric field, more is the charge, and more is the charge even at the interface. And you also see that there is a difference between the amount of charge that is being accumulated in the polyethylene and the epoxy, and that is because of the material difference. The material which has a larger density of charge, which is polyethylene in this case, density of deep traps is higher in polyethylene at the interface than in the bulk. As a result, this interfacial peak is kind of shifted towards the polyethylene rather than the epoxy, because the density of deep traps is higher in the polyethylene right next to the interface than in the bulk. And that is because of the crystallinity, a comparative crystallinity of polyethylene and epoxy. Polyethylene has a lower conductivity than epoxy. So what I have tried to show you here is that when we are doing space charge measurement, there are many parameters that we have to take into account. And this is especially true when you are making measurements in dielectric systems which have more than one material in within it. There are more than one materials. When there are different layers, many things come into the picture. And the interpretation of the pulse electroacoustic signal that you see has to be very carefully done. Calibration has to be very carefully done. And space charge measurement is quite a challenging task. But once you do that, it can be very useful in design of the insulation as well as in condition monitoring of the insulation. I will stop here and I'll take questions. These are the references that I have used. The case study that I have pointed out, I have only very briefly discussed it. This comes from our paper in IEEE, where we discuss many other things.
Thanks, Ben, for an in-depth discussion on the theories of space charge. So we already had the first question discussed, so I will go to the second question by Naresh. Can we refer the charge accumulated below the threshold level of the material as surface charge?
I think I somewhat answered this question as well. No, surface charge is charge. I'll just put it this way. You have a surface. Let's say I have a corona here. The charge is here. It's free charge. And it's sitting there because it's nowhere to go. The dielectric does not allow conduction. So the space charge sits there. It's free charge, which is resident on the surface, physically resident on the physical surface of the material. That is surface charge. And when we are talking about threshold fields, there will be no charge accumulated below the threshold field. It is as simple as that. I mean, ideally speaking, when you are at fields, let's say, as I said, epoxy resin has a threshold field of 18 kV per millimeter. If you are at 10 making measurements at 10 kV per millimeter, there is no charge which will be accumulated. All the charge that you inject will nicely go away. It's like a crowded room. And there are no chairs to sit on. So you enter the room, you find no chairs to sit on, you just go out. Yes.
Okay. Vaibhav asked, what is behavior of space charges in vacuum when it is used as dielectric medium?
Okay, I have to again repeat what Professor Raju said, that when you have vacuum, if you have ideal vacuum, you do not have any charge. And if you have charge, it must come because of remnant gases. So it will behave exactly the same as remnant gases. But a thumb rule could be that if you know that that space charge is accumulated, figure out what is the field due to the space charge and look at the field modification due to the space charge accumulation. That will give you an idea about what will happen.
So there is no chance of accumulation of space charge in vacuums?
Ideally speaking, no. See, when we talk about vacuum, we are talking about vacuum. But practically, how can you have vacuum? You cannot.
Yeah, of course.
When you talk about vacuum, you're talking about very low pressure levels. If you're talking about very low pressure levels, pressure of what? Air? Or maybe some other gas?
Yeah.
That's what I meant.
Balaji asks, you had explained about how electrons propagate. Can you explain how holes propagate?
Yeah. It is holes propagating means vacancies propagate. So if you have defects, if you have impurities, there will be unfilled positions in the ionic lattice. And due to interaction with the mobile charges, this lattice, the lattice doesn't move, but the vacancy moves from one lattice to another. And it might so happen that one such vacancy might trap an ion which is present. An ionic carrier which is in its vicinity can trap it, and you can have ionic trapping.
Okay. Nilesh asked, in same material interfaces, what are ways to remove out negative polarity charge which evolve in the joining phases?
Same material interfaces, yes. Yes, that is again something that Dr. Kasim will be able to tell you because he spent a lot of time doing that, but I will tell you. When you have same material interfaces, like I showed you in case of epoxy, we did two things. I did not spend so much time on that work, so let me elaborate on that a bit. We did two things. We took two epoxy layers. And we just pressed them very hard against each other. In that case, we saw a lot of charge accumulation. And we realized that no matter how hard you press, there is an infinitesimally thin layer of air in between. And because it is very thin, the chances are, firstly, that it is very highly stressed. It is even possible that that air layer was ionizing and we were getting very high charge densities. So the next thing that we did was, so that gives us the one pointer: remove every possibility of any kind of debonding. So the next thing that we did was we took the two epoxy layers and we bonded them very nicely to each other. And even then, as I have shown you, there is interfacial charge. This interfacial charge begins to accumulate, which was puzzling because why would you? It is not due to the disparity between permittivities or disparity between conductivities. So what is it due to? So the only hypothesis that we had was it must be due to the material, the surface. So you have the two layers, you create the two epoxies separately, and there must be some morphological changes at the surface which has resulted due to the manufacturing process. There must be something happening at the surface where there is a material kind of accumulation of morphological changes at the surface, and this has resulted in traps, and that is causing surface charge trapping. So afterwards, this was part of Dr. Qasim's work. When he worked with functional materials, he had the same problem. And he was able to solve this problem very nicely by using hot compression. He'll talk more about this. So what we did was we took the sample and we bonded them together. And after that, we applied temperature and compressive forces. And and that had to be kind of fine-tuned. We had to figure out what kind of temperatures to use, what kind of compression to use. It cannot be more, it cannot be less, etc. And as a result, we were able to kind of modify the surface property so that the layer became as far as space charge is concerned, it became uniform. And after that, we did not see any space charge accumulation at the interfacial layer. So that would be an option. In practical situations, this is only possible at the manufacturing stage. This kind of conditioning may not be possible in equipment already in service, but this is a way where you can remove the interfacial charge. So some kind of conditioning needs to be done.
Okay, thanks. So if there is any further question, you can raise your hands. So I guess we don't have any question more. Thank you, ma'am, for your talk.
Thank you, King.
And we will have our second talk in 7 minutes. So it's from 11:30.